Today is the last day of this 10-day intensive quantum computing internship program, right? So 10 days ago, quantum computing was a distant headline for you guys, right? Today, you guys have run a real algorithm in real hardware, real quantum computer, built entanglements with your own hands, searched with Groover, and beaten classical computer, right? So you have simulated molecules and caught eavesdroppers using nothing but physics. More than that, you guys asked sharp questions, debugged real problems, and you guys pushed through the parts that didn't even click at first, right? So the curiosity is the real skill, and it will carry you forward beyond this program. So you are not just learning about this field anymore, you're part of it. So stay curious, keep building, go shape what comes next. And congratulations. I am really, really proud of every one of you guys. Let's go and start the demos today. So let's go ahead. First, let us see who's Aditya. Let's go with Aditya from the alphabetical order.
If it's okay, can I go in like sometime?
Okay,
Because I need
so
to
that's
fix
fine.
something. Yeah,
Sure,
okay,
sure, no
thanks.
problem. Aparna, you want to go next?
Okay.
Okay, go ahead.
Can you see my screen?
Yep, we can see your capstone project.
Okay.
Great.
So, hi everyone, my name is Aparna, and my capstone project was about finding a stable molecule with quantum computing. So this was basically like a combination of the third and fourth project choice that was there. So like simulating a hydrogen molecule and also using the Grover search algorithm to like find different lengths. So the central like problem or issue that's there is that it's really important to find stable molecular configurations in like chemistry, nanoscience, and like different fields of science. And so what this project does is it finds the optimal bond length of a hydrogen molecule. And I will explain this later, but for it to be stable, it has to be a strong bond without being too repulsive, and it also needs to have the correct amount of energy to where it's not too overpowering. And so this was the process that I followed. So the first step I did was I used this equation, and this basically represents the total amount of energy or like how stable it is. The R is the distance between the molecules, and then 0.74 is the optimal length in angstroms for H2, and the optimal energy that corresponds to it is 1.14. And this is like, it's proven to be that, but to like use code to actually prove that, I tested different bond lengths from 0.3 to 1.5. And so the package that I imported, scipy, it tried those R values, found the lowest energy levels, and then it confirmed that 0.74 was actually the optimal value for H2 for it to be stable. And I generated this graph. I did have to use like Python, like pandas and stuff like that to like refer to syntax that I didn't know. But data science and like generating graphs is something I have experience with in Python, so I was able to do that pretty easily. I'll show you my code in a bit, but so on the left side, it shows that there was a really low distance, which meant that they were very repulsive since they were close to each other, and it showed that there was a really high energy. And then on the right side, it was a lot more distance, so it had a weaker bond, and it also, since it was trying to be closer, it had also a high energy. And the only point that was actually balanced and had a balanced repulsion and the lowest energy was this point, which was 0.74, and it had negative 1.14 joules of energy. The second point was using Grover's search algorithm. So I basically wanted to prove more that 0.74 in all instances in quantum computing is basically like it gives you the most occurrences. And so these values were like lengths of the molecule, the distance between the molecules, and these were converted into qubits and then just used a normal like circuit. I referred back to the class where we actually did the Grover algorithm and like used some code from that. And the diffuser basically amplified its probability, which means interference was used to like make the right answers even more right and the wrong ones even more wrong with constructive and destructive interference. It ran 1,024 times, and then the state 011, which was 0.74, ended up being the value that had the most occurrences. So it just proved it more. And then to like further support Grover's search algorithm, I changed a bunch of the probability of the findings for 011. And so it was like an iterative process, and after doing like one iteration, it was like a pretty low value of occurrences for 0.74. And then once I did two iterations, it jumped to 94%. And then again, it started dropping once I did more iterations. So that just proves overshoot and how like doing a certain amount of iterations will get you to that like optimal maximum point, but doing too much is gonna like bring it to the stopping point.
Yeah,
and
that's
then
called overshoot, right?
yeah, so this was my code, and this was like the first initial equation that I had to use, and then so the most stable bond length was just printed there, and then I made an array to plug in all the different lengths, and then like I said, I had experience with graphs and stuff, and so I printed out, and the reason it's like a U graph is because of it being quadratic, and so yeah, and
So quick
then
question, Aparna there.
yeah,
So based on, so you need to find an optimal way of like optimal place where you can have the distance, the bond distance will give like more energy and more thrust, something like that, right?
yeah, like stable to where it's
Stable
not,
energy. Okay,
yeah,
awesome. Yeah. So using this algorithm, you can find out like at what place it's going to be stable, right?
exactly, and at what like corresponding energy, because the lower the energy, the more stable it is out of this like,
Stabilities.
data set, yeah. And then this was again the circuit for Grover search algorithm that I used from like our lesson.
Mhm.
And then it printed out this, and each qubit corresponded to like the value of the length. And then again, this was the probability thing that I also referred back to from our lesson, and then
Yeah.
printed out the iterations and the graph.
Yeah.
I just have like one more slide. So mostly what surprised me was that the overshoot was a lot dramatic than I thought it would be, and also 0.74 was a consistent answer throughout the whole thing, so I was really surprised by that. I didn't know it would be so accurate. And so this project was important to show how like researchers could use like a simulator, because I didn't use an actual like molecular energy model, so they could use that before they actually go on to building and testing. And so what I would do next if I got more time would be to use like an IBM quantum hardware or like something more complex, since this is a very like basic representation of like research and stuff.
Mhm. Awesome. Wonderful, Aparna. You did a great job.
Thank you.
Awesome. You covered like pretty much all three samples like that we discussed, all three different applications. Wonderful. Good job. Very good job.
Thank you.
Yeah. Okay. Who will go next? Soham, are you ready to show? You have an issue with mic, Soham?
Oh, can you hear me?
Yeah, we can hear you. So
All
are you
right.
ready to show something today, or you want to skip?
No, I can show. Yeah.
Okay, go ahead.
Give me one second. Let me try to share my screen.
Yeah.
Okay. All right. Can you see my screen?
Yeah.
Okay. So for this project, I kind of like went through the Grover search using the first option given for the capstone project. I
Mhm.
used quantum search for optimal trading strategies. So in hedge funds, there's a lot of trading strategies, and you have to choose between a lot of them. For example, firms like Citadel or Seeking Zero, they have like over 1,000 different trading strategies, and they have to choose between them. They use that. They usually choose the trading strategy with the highest Sharpe ratio, which is a financial term that tracks the risk versus return of the strategy. So this project uses Grover search in order to find the best strategy, given that all the Sharpe ratios are given. Okay, the search problem is that the classical approach here actually tests individually. So, for example, wait, sorry. Yeah, for example, if there's 16 strategies, and there's 16 different strategies, then it will take the probability of each one because it'll go through one of them at like each time. So the probability of that would be 1 over 16, right? Since it would be over probability of 1 over 16, the search time grows linearly. For example, if there's like a million strategies, um, the computation thing, you need a lot of more like computational power in order to calculate all of this, which takes a long time, right? And then, and actually the Grover search is faster because it's the square root of n, so it leads to a much faster approach to solve this. And then I use the Grover search in order to do that. So one second, yeah. So I use the Grover search to do that. And then here's my coding. I can explain the code. So for example, this one kind of creates, yeah, so I just imported the basic libraries here. And then here I created the multi-gate Z function, which is the Oracle helper in the Grover search. So for example, the Grover search, what it does is like we give it the correct answer kind of thing. Um, for this example, I just fed it a number like 1011. I gave it this solution, but usually the firm what it'll do is it'll make a function that kind of gets the correct answer by itself. And once the oracle is created, each round the diffuser makes the amplitude greater for the correct answer, so it increases the probability each round. So that's what I did here. And then I gave it the different rounds, and then I gave it the correct answer, which is the target, and I give it 10 rounds for the sake of this project. And then I calculate the probability in a list. And then to graph this simulation, I just use the basic libraries, and then I define the gates and probability, and then the same thing n over 4, and I graphed it using the PLT plot functions. And then after I graphed it, I saw that the best solution was at 3. The best solution was at 3, and then as I went through more, the more I overshot it, the probability changed. There was a random spike at 9, but then after that, the probability kept decreasing. And then I think the reason for that is because the Grover search, what it does is it like makes the correct answer more correct every time you go from the algorithm. But then the more you overshoot it, it actually starts decreasing from the optimal point. So for explanation, it's kind of like a 2D like axis. So for example, it's getting more closer to the correct axis, but then the more you overshoot it, the more farther it gets from that. And then here's the equation I used to calculate the theoretical thing. Using the math side, it was a pi over 4 times the square root of n for the theoretical solution. And then we defined it as n over 4, so I set that equal to it. And then using math, I got that the theoretical should be 3.14, and then the algorithm actually matched the same correct solution. So every round, it found the oracle using diffusion, it increased the probability, and then we got the correct answer as 3 because the more we overshot it, the lower the probability the correct answer went. And then after we did that, the oracle actually marks the answer by reflecting the gate. So then the x would be negative x, and then using that we got 3. So the more real world importance for this project is that it can be used for database searching, scientific computing, and AI and cryptography to make things more secure. And it can be used for more other various things in real life, such as the ones listed below. The final takeaway I got from this project is that if I had more time to improve this project, I would make this a custom software where people got to choose the number of qubits initialized,
Mm,
rather than having its standard like already given.
mm,
And then I would compare multiple problem sizes. For example, I'd compare up like strategies with like for example 8 strategies and 16 strategies and 32, and show like certify even more that the optimal peak moves later as the
mm,
search space grows. And then I could have probably animated the graph here. Like I
mm.
could have animated like you type in the number you want and it show like dynamically.
Yeah,
And then for four, to connect it to real finance more, I would simulate profitability scores and show how Grover's algorithm could find the best strategy faster than brute force. So I could compare using the standard computing model. And then the final takeaway I got from this project is that the Grover's algorithm is not about just faster search. It's about kind of having a more controlled application using quantum interference. And the
mm,
thing where most people get it wrong is
mm,
that they assume that the oracle
mm.
finds you have to kind of give the oracle kind of a defined answer.
Logic.
The
Mhm,
usual myth is that people think it already knows it, and then
mhm.
um, that's why Grover search is really fast because now the computer already knows the correct answer and it goes through all things at once. But the actual truth is you have to kind of give it a defined parameter for that,
Yeah,
and it's extremely faster because the square root of n makes solving for database searching and better strategies really, really efficient compared to the computational method.
yeah, yeah. Wonderful. It's a great job. So can you replace Oracle with a machine learning model?
Yeah, you can kind of give instead of the oracle like I gave 1011 for this sort of basic project, you can kind of give it its own model to
Yeah,
test each strategy out, and then um you have a program to find the correct answer.
yeah.
I searched that up, and then that's also what uh, AI told me that you can kind of do that instead.
Yeah,
But for
yeah,
this project, I just gave it 1011 for the sake of simplicity.
yeah. Excellent. Wonderful. Soham, I am really impressed. This is
Yeah,
great. See, within
thank you.
just 2 weeks and within few days, you guys are able to achieve so much. Like I I can't be more proud of you guys. This is wonderful, guys. Okay, awesome.
Yeah, and then the math behind it,
Hmm.
I used the simple like simple math like square root of n, and then the formula given here to calculate the theoretical ones. But then while I was researching, it had a lot of more like when I tried to delve into the math, there was a lot of more math going on, which is really advanced. Because the reason why the Grover search algorithm works the way it does is it's actually kind of it's a periodical function, but it's really complicated. So I couldn't get more into it. But there's a lot of
Yeah,
math formulas and it was getting more complex as I went through. So,
yeah, yeah. See, as you increase the number of qubits, the complexity will increase, right? See,
yep,
see the fundamental thing with the qubit is if you use just a bit, you have either 0 or 1. Only one possibility, it could be either this or that. If you use 2 bits, you have four possibilities: 0, 0, 0, 1, 1, 0. So you have only one of those four possibilities are possible, right? But if you
yep,
use the same thing qubit, all four at the same time are possible,
yeah,
right? So you cannot say, oh, this is only the answer. You have like four different answers at the same time.
yep.
So when you
And
measure it, it will give you the answer.
yeah, and then sorry, one last thing I found really interesting while doing this
Hmm.
is that the actual geometry, because my explanation was kind of how Grover's algorithm is the correct axis and it goes closer to it, but then you
Hmm.
push it farther and it goes farther from that correct axis. So then the axis is actually defined um according to the math, it's like theta equals to arc sine 1 over the square root of n, where the
Yeah.
state angle is 2r plus 1 times theta. So that's where the actual kind of the geometry axis is there. And then using the first equation for the probability of the correct answer is like sine squared times 2r plus 1 theta, and then it shows like when I graphed it on Desmos, that actually showed the like how it's getting away. So it's like a really like mind-breaking thing because like I like math more, and then like
Yeah.
delving into the more complexities kind of was really interesting in this project.
Yep. Yep. Awesome. Awesome. So you guys can spend like your summer little more things into this, and then you can make it like a software product, right? In the future. That's
Yeah.
awesome. Wonderful. Okay, so who's next? Let's see. I skipped like in the middle few people. Let's say next one is Jay Hari. You want to try? Are you ready, Jay Hari?
Yeah, I just
Okay,
have a.
okay, okay. So after Jay Hari, well, Kushal, maybe you can get ready. Okay.
Good morning. Today
Can you hear me?
Yes, good. Go ahead.
we are going to be talking about visualizing Groover's quantum algorithm. Let's look at how classical and quantum computers approach searching an unstructured database. A traditional, classical computer uses linear search. It checks every single item one by one. If you have n items, it takes up to n steps. As data grows, this method completely bottlenecks. A quantum computer uses Grover's algorithm to change the math entirely. Instead of searching sequentially, it looks at multiple possibilities at once and amplifies the correct answer. This creates a quadratic speedup, reducing the work from n steps down to the square root of n. To put that in perspective, for a database of 1 trillion items, a classical computer needs a trillion steps. A quantum computer needs only 1 million steps. That is the shift from years of compute time to just seconds. The core of Grover's algorithm relies on a repeating two-step cycle, the oracle and the diffuser. First, the oracle acts as a tagger. It uses controlled Z gates to isolate our target item by flipping its mathematical phase. Second, the diffuser acts as the amplifier. It uses Hadamard, Pauli X, and multi-controlled Z gates to perform a mirror flip. This operation shrinks the wrong answers and forces our tagged target to stand out. We simply loop these two steps until the correct answer is ready to be measured. Now that we have the theory down, let's jump over to Google Colab and run the actual circuit. Once in Colab, we enter the target value we are searching for and the calculated number of iterations. With those set, we can execute the circuit. This graph plots success probability on the y-axis against the number of iterations on the x-axis. The red dotted line marks the optimal point where constructive interference maximizes the target state's amplitude before it begins to overshoot. Here's a simple histographic representation of the same. In conclusion, Grover's algorithm transforms unstructured searching by replacing sequential guessing with quantum interference. By finding the exact peak before an overshoot, we achieve a definitive quadratic speedup that turns classical constraints into quantum efficiency. Thank you for watching.
Awesome. Very good. Very good job. Okay. So next, who? Kushal, you want to go next?
Sure.
Yeah.
Can you see my screen?
Yeah, we can see Kushal.
Okay. So my project is called Catch the Spy. I just catch the spy, and it demonstrates through the BB84, which we briefly went over in day 7.
Hmm.
Give me a second. I can't see my own presentation.
Yeah, it is. Looks like it is loading.
Oh, okay. Okay. So, the BB84 is a quantum key distribution, which means it's a very secure way for two people to share a secret digital key through physics and not math. So the randomness doesn't come from a math formula like a classical computer. Instead, it just comes from the quantum environment, the physics world. Um, So this was my overview where I connected to what we learned in class. So my project followed the basic prepare, manipulate, and measure.
Mm.
So we have two people, Alice and Bob, and they're trying to share two keys, and then Eve is going to be the eavesdropper, and we're going to see if the calculated qubit by Bob has been changed. And if there's a change, that means Eve has measured it because what we learned is that when a qubit is looked at measured,
Mhm.
it disturbs the qubit because we cannot just measure while it's in superposition. When we measure it, it um,
Yeah.
uh, chooses a final state.
Yeah.
So Alice prepares the qubit, and then the qubit may be disturbed by the Eve, which
Mhm.
we're gonna see later, and
Mhm.
then Bob measures it.
Mhm.
So we learned that the measurement collapses a qubit, and this is the main reason that Eve gets caught.
Mhm.
So if you realize there's some discrepancies in the qubits being measured, then we know that some like an eavesdropper was there.
Mhm. Yeah.
And then in my code, I also used the X gate and Hermite gate. So I used X to encode a 1, and
Mhm.
then I switched between H and Z
Mhm.
on the X-axis to like see what the probability was.
Mhm.
I'll go over the code and the graphs in a minute.
Okay.
So let me just skip to this slide. So I ran the four algorithms that you had shown us, and
Mhm.
something that I found was in common that
Mhm.
all four algorithms used superposition and then interference to get a probability that would which was just amplitude squared, which was then manipulated to get the correct answer or to get a specific answer.
Mhm.
And it was shown through Deutsch and Hose where they used multiple n qubits instead of just one.
Mhm.
And then it was also in Grover program where it amplified the search algorithm.
Mhm.
And the Shore one was where it threatened the encryption
Mhm.
by combining the quantum like it combined the quantum safety with factoring, which was a classical thing.
Mhm.
So in my code, when I ran, this was when I purposely made it with no Eve.
Mhm.
And then this is the ideal computer. This is what ideally it would have run. The error rate was 0%. So we could see that, I mean, there was one no, but rest of them was yes.
Mhm.
We could see that whenever Bob received the qubit originally and they
Mhm.
compared it publicly, there was no much different. There was no difference at all. This means there was no eavesdropper in that case.
Mhm.
But when I ran with an eavesdropper,
Mhm.
you could see the error rate was 25%. And then I started to wonder, why is it not 50%? Because the Eve is just like Bob. It chooses a random base, and
Mhm.
then if the Eve gets it correct, then the qubit doesn't get manipulated or changed. But
Mhm.
because it's a 50% probability of her choosing the right one, it's also probable that it makes a disturbance in the qubit. So the reason the error rate is 25% is because the probabilities multiply together.
Mhm.
The one half from what Bob is choosing and the one half from what Eve is choosing gives a probability of 1/4, which is 25%.
Mhm.
Now, when I put this into a graph, you could see that the no Eve ideally gave 0%, and then with Eve gave approximately 25%.
Mhm.
Now this was just Um, I plotted in a histogram to see how the probability went.
Mhm.
Now, on the bottom over here, no Eve was always 0.
Mhm.
That was ideally because the qubits never changed. The error rate between with Eve fluctuated a little bit. It went to 30, 20, but mostly it was in the
Mhm.
25% range if we take an average of it. At the end, I like the quantum computer. I couldn't run it on the actual quantum computer because there were too
Mhm.
many requests going on.
Okay, okay. Yeah,
But
actually, if you run
what I
this
was
in, if you run this in IBM quantum computer, you will see a little bit difference because uh, because the quantum computer that what they provide, it's not in an ideal situation, right? You'll see a lot of interference.
Right.
So error rate is going to be a little more. You'll see the actual result is much, it's a little bit different than what you have it in a simulator.
Yeah.
Yeah.
So, well, I was gonna talk about that a little bit further on the last slide.
Okay,
But
okay.
just going to the how it connects to the core concepts we learned in class. So as we saw when we ran the clean BB84 with no spy, Alice chose the random bits and the random basis, and then Bob chose it. And then they keep only the positions where it was matched. And since there is no Eve, and this is ideal, the error rate should be around zero, which it was.
Yeah.
And then when Eve appears in there, it intercepts each qubit and measures it on a random basis. So the problem is if Eve chooses the wrong basis, she changes the state of the qubit. And then when Bob measures it, the error appears in the new key, which was manipulated. And that's why we saw it on the graph.
Yeah, that's why you see only 25%.
Yeah.
Yeah.
And then so going on the reality on why on the actual IBM quantum computer we would not see this ideal thing is I would expect some small error even without the Eve because the quantum computers we have today are a little bit noisy. And something I researched about was NISQ. So these people are more into the modern quantum computing. They're trying to implement new ways to get more qubits, and then they're investing heavily on this types of investigation and area. So the machines are real and they're useful for learning, but they're not perfect yet.
Yeah.
Which is still, I probably predict decades away because the noise might still be there.
Yes.
Finally, my takeaway was that quantum computing is just not about speed. Like, it's not about how it runs square root of n times faster than a classical computer. In fact, it's the power that comes from the randomness of physics itself. So it used concepts from physics and not math because math, as we talked in class previously, it's not really random. It uses a formula to generate a random number. But when we use physics, when quantum computer generates a random number, it is genuinely random, which does not only help us to keep encryption, but it also helps us to break encryption
Yeah.
by algorithms like Shor's
Yeah.
algorithm or to find something in a really big stack like the Grover algorithm. So a spy cannot, my final takeaway was that a spy cannot measure without leaving like a little bit trails
Trace.
behind
Yeah.
with the measured qubits. And this was
Yeah.
interesting when I saw, and the graph suggested the same about the error rates and what I had measured.
Yeah. Wonderful. It's awesome.
Yeah,
Very good job,
thank you.
Kushal. Yeah. So one thing I want, so it's very interesting. I don't remember mentioning this. Like, if you want to compare this classical computers and the quantum computers, you mentioned that both are for two different purposes, right?
Mhm.
So just to give you a quick analogy, you can say a regular classical computer, like your laptop or a desktop, you can say it's a kind of a motorcycle or a car if it is a little bit bigger. And if you take like a little bit bigger computer, a supercomputer, maybe it can come, you can compare it as a train, a big train, right?
Mhm.
And when the same thing, if you want to put like where the quantum computer, you can imagine that's a aeroplane or a jet plane, right? So you cannot use a jet plane to just go to your neighbor's house or maybe another street, go and get the groceries, right? You have to use
Right.
car or a motorcycle. So for those kind of things, classical computer is ideal. You cannot use a quantum computer for classical problems.
Mm.
But if you want to go to a different continent, if you want to go by car or it takes like years, right? So for those kind of things, you need quantum computing. So that's the one analogy that I wanted to mention. Okay, awesome. Next, who's next? You are Jay, Jay Shri? Jay Hari. You're Jay Hari, right? Sorry. Uh, let's go next. Who wants to do next? Uh,
I can go.
Go ahead, Aditya. So after Aditya, we have Kushal. You're already done. Shravya after that. Okay.
Can you see my screen?
Yeah.
Uh, yeah. Okay, so good morning. Today I'm going to be presenting my capstone project, which is about simulating the hydrogen molecule. I chose this because I do have experience with chemistry, and I thought it would be kind of cool to dive in deeper and integrate it with quantum computing. So the goal today was to simulate the molecule and find its lowest possible energy state, which is the ground state, using a quantum algorithm called like VQE, which stands for Variational Quantum Eigensolver, I believe.
Oh.
And so the reason this kind of matters is because molecules are like quantum systems. Uh, Instead of approximating nature using classical computers, we can just use quantum computers uh, that follow the same rules. Hydrogen is the simplest molecule, and it's the target value is about negative 1.137 Hartree, which is yeah the ground state. So this is kind of a flowchart of how the whole thing works. Uh, so this kind of combines quantum and classical computing. First, a quantum circuit creates kind of like a prediction for the molecular state using a parameter which we defined as theta. And then we then measure the energy of that state using the Hamiltonian of that hydrogen molecule. And then after that, we use the classical optimizer, which looks at the result and adjusts the angle to try to get a lower energy to get the ground state essentially. And then we just repeat this again and again.
Mhm.
Okay, so these were the results. So after running the algorithm, and like this happened like multiple times, we got a result extremely close to the known value of negative 1.137 Hartree. What does mean? So basically, the algorithm successfully found the most stable configuration of the hydrogen molecule, which is the ground state. In the graph, you can see the valley is the bottom of that valley is the ground state energy, which pretty much matches the known value. And you can see like up to like 6 decimals, we had like an error of 0. Uh, yeah. And our best angle was negative 0.224 degrees. So what was surprising was that a circuit of only 2 qubits can approximate like a molecule. Uh, the quantum and classical parts were together to simulate the molecule. Uh, the predicted value was extremely close to the known or accepted value. And yeah. So limitations. So right now we only simulated hydrogen, which is still like the simplest molecule. Real world molecules are like still much like bigger, and current quantum hardware has limitations, say like noise and vibrations. Uh, so in that, like in the future, we could like learn to and try to like to simulate larger molecules by improving the quantum like hardware, and then we could run this on actual quantum hardware. If I had more time, I could try that. But yeah, and then we could also use this to explore certain molecules in like batteries, like cells, and even in medicine, which could prove extremely helpful in. But yeah, which proves it can be extremely helpful in like multiple industries. Yeah.
Yeah, it's wonderful. Is that all?
Yeah, that's it. I
Yeah,
can show the
that's
code.
one. Yeah,
Oh,
that's a wonderful. Um, so see, with this, you are able to simulate that hydrogen molecule and where the stable condition, right? The stable where it is
yeah.
stable, right? So
Yep.
hydrogen and oxygen, these are all really, really important for everything, right? So
Yep.
with energy related stuff like food related, like vegetation, all for everything you need hydrogen. So if you find like how you can make a hydrogen molecule stable, if you can find those conditions, maybe you can do more, right? So this is a very real good understanding of like the entire molecule using a quantum computer. Yeah,
Okay.
wonderful.
Thank you.
Yeah, who's next? Um, I think we are Aditya. We're done. Aparna
Can I go
done.
next?
Jai Hari. Yeah, go ahead, Kam. And we have Sharanya after that.
Can you guys see my screen?
Yeah, we can see Kam.
Okay. So my project was the Grover's watches search. So um, for the Grover search, the way it works is when you have a list with a certain amount of items in it, it instead of going through each one like a classical computer, it puts all the items in a superposition using the H gate and uses phase to flip.
Kam, we can't see your slide presentation. Are you presenting something or we see a desktop?
Oh no, I'm just presenting my code.
Oh, okay.
So the way Grover works is pretty simple. It only has two steps. So you have the oracle and you have the diffuser. The oracle marks the right answer and the diffuser amplifies it from the rest of the items. So I already got all the basic uh, things required set up and downloaded.
Hmm.
And I first started out with placing all the qubits in a H gate, or so giving them equal probability. And then here's the Oracle. So the way the Oracle
Are
works is
you are
pretty
you
cool
sharing your
because
screen, Cam? We can't see your screen. We see your desktop, but only the desktop background image we can see.
oh, now can you see it?
It's still loading. Yeah, now we can see. Awesome. Go ahead.
Okay. So first I put all the qubits. So there are four qubits. For the in the capstone project, it said I should start with four qubits.
Hmm.
So I put all the qubits in the H gate, and then next is the Oracle. And the way the Oracle works is that it applies a phase. So you have the multi Z gate,
Hmm.
and And then you have the diffuser,
Hmm.
which amplifies, like I said, the right answer.
Hmm.
And to find the probability of measuring the right answer is I use the state vector, and the state vector it extracts the amplitude of the qubits, and with the amplitude, you could measure the probability by squaring the amplitude.
Hmm.
And um, for the visual, so like I said, I started with 4 qubits, and I wanted to find the item 1011, and I put a maximum round of 10. So what this 10 means that it's going to do Oracle diffuser 10 times, and it's going to find the highest probability. So after 10 rounds with 4 qubits, you can see that it peaked around 92.2% at round 9. And it also peaked around round 3, which is pretty cool because there's this interesting formula, which is pi over 4 divided by square root of n. And that tells you the optimal amount of rounds you need to find the highest probability of mentioning the right answer. And since there are 4 qubits, that means there's 16 possible items because 2 to the 4 is 16. And so when you do square root of 16, which is 4, multiplied by pi over 4, that's around pi. Pi is equal to 3. So you can see that the theoretical maximum or optimal rounds is 3. But in reality, when I simulated it, I got 9. And this gray line over here is the random guess. So if you were to randomly guess to find the right answer, that's 1 over 16,
10%.
which is over here. Yeah. And then to personalize it, I added 2 features, which is where one let the user choose the number of qubits and what the target number should be. So, for example, I ran it before presenting, so I chose 7 qubits, and I chose the target number to be 111111. And the cool thing I found out is that when you increase the number of qubits, or the curve actually becomes much smoother. And the second feature that I added was this red line over here. That red line, like I said, is the maximum theoretical probability, which uses the formula, should be right here. Formula pi over 4 times square root of n. And that's a theoretical probability, but the maximum probability over here, which is in green, is peaked over here, around round 26. Yeah. And it kind of looks like sinusoidal because, again, like many people have said, it overshot because once it found the right answer, it continued to amplify the other wrong items in the list, and that kind of made the right answer become mixed in with the noise, and slowly, and the probability of mentioning the right answer slowly decreased. And that was all. And like I said, the cool thing I found was as you increase the number of qubits, the graph becomes much smoother. And one possible application I came up with yesterday was that you can use this Grover search in astronomy, because in astronomy there are data sets that contain millions of like data on celestial objects, let's say pictures. There are probably thousands and thousands of pictures about stars or planets, and scientists are trying to categorize or trying to find a certain object in that list. And it takes a long time with classical computers because there's so much data. So the way I was thinking was you could use the help of AI to classify the image when it's first captured, and then that will give it a label, like a 4-digit label, like 1011. And then with the label, you could use Grover search to find for a specific celestial object.
Yeah. Awesome.
And yeah, that's it.
Wonderful. Excellent. So if you take, this is like 7 qubits, right?
Yeah, 7 qubits.
So if you take like 10 qubits, so this is all you're simulating in your laptop, or maybe whatever the server that Colab connected to, right? So you can go up to maybe 10 qubits, and after that, our classical computers won't be able to handle it. If it is a supercomputer, it can handle up to 20 qubits. Right? So after that, the simulators won't work. So if you want to try with like a 30 qubits, you can try with the IBM quantum computer. So if you still have like a minutes left in there, you can try with 30 qubits and then see how it looks. It takes like it won't take long to run, but you'll get an idea. Just try over the
I'll try
holidays.
that.
Yeah, wonderful. I really like it. So you practically experimented that with, and then sure. Wonderful, awesome. Okay, so we have almost like 3 more minutes. Shreya, you want to show?
Well, I can go.
Okay, good. Oh, Shravan, go ahead.
Yeah.
Yeah, Shravan I wrote. Shreya did not opt for it. Yeah, go ahead, Shravan.
Yeah. One sec.
Wonderful, guys. Like within 2 weeks, you guys are able to do that much. That means if you guys spend a semester on this, I can't imagine what you can achieve. So good job.
Not letting me share.
Yeah.
I have to leave the meeting and then join back. One
Okay.
sec.
Okay, no problem. Anybody have any questions on any of the presentations so far? You guys can ask questions to each other also. So yeah, I want to see like simulating the hydrogen molecule in quantum computer and then see how it looks. So who did that? The hydrogen molecule thing? Kushal? Not Kushal. Who? Jay? Jay Hari? Are you the one who did that hydrogen molecule? Jay Hari, you're the one, right?
I think it was Aparna and Aditya.
Aparna
Yeah,
and Aditya. Yeah,
yeah,
I
yeah.
think Aditya also did. Aditya's one is Aparna did like 3, 4 things. Yeah. Okay.
Can
Go
I
ahead.
start? Okay, so hello everyone. My project investigates whether the performance of a quantum computer can be predicted using its hardware calibration data. So, quantum computers have the potential to solve certain problems much faster than classical computers, but the problem is that they're extremely noisy. So, even small errors in the hardware can significantly affect the accuracy of the computations. So my research question is, can hardware calibration metrics such as T1, T2, and error rates be used to predict quantum circuit fidelity? So to investigate this question, I use real quantum computers provided by IBM Quantum. I tested the three different quantum processors,
Mm,
uh, and for each processor, I created a Bell state circuit. A Bell state is one of the simplest example of quantum entanglement and
mm,
provides a useful benchmark for measuring performance. And so each circuit was run 4,000 times to obtain reliant measurement statistics. So for every quantum processor, I collected several hardware calibration metrics like the T1 relaxation time, which measures how long a qubit retains energy,
mm,
T2 coherence time, which measures how long the quantum information is preserved,
mm,
readout error, which measures measurement accuracy, gate error, which measures how often the operations fail.
mm,
And then I also calculated Bell state fidelity, which measures how close the experimental results are to the ideal Bell state outcome. So how different the actual quantum computer is from the expected results.
mm,
And then these measurements were combined into a data set for analysis. So like this is my actual code.
mm,
Uh, I'll explain like the main parts of it.
mm,
So first of all, I imported the libraries and then connected to the IBM quantum computer, and then I chose multiple quantum computers so that it can be tested on all of these computers and the results can be compared between those computers. And then next, I made a code to loop through all of the different computers so I don't have to write it for each one. And then so first I created a Bell state over here,
mm,
and usually the result is either 0, 0 or 1, 1.
mm,
But if any other outcome appears, that's obviously caused by noise in hardware.
mm,
And then I transpiled the circuit
mm,
because the quantum computers don't understand gates like H and CX. So the transpilation converts the circuit into the native gates. And next, I ran it 4,000 times. Each run is a shot, and more shots give better statistics.
mm,
And then fidelity is how it just calculates how close the real result is to the ideal Bell state. And uh, and then I calculated the um, calibration data
mm,
using this is basically how I calculated the calibration data.
mm,
So, and then for every qubit, the it stores the backend, the timestamp, for example. This is the data set
mm,
where it stores all of these different things,
mm,
and you can see that like um, uh, the bell fidelity it changes depending on the. I tested these for 156 different qubits for
mm,
each one,
mm,
and then you can see how the bell fidelity changes based on these metrics. So uh, the point of this is the next steps
mm,
are to get you get these statistics and then you try to build
mm,
a machine learning model.
mm,
That's my plan to build a machine learning model
mm,
to predict when the errors will happen.
mm,
And then uh so yeah, so after you build a predictive machine learning model,
mm,
it could estimate the quantum circuit fidelity using only the hardware measurements.
mm,
And then ultimately, what I want to do is it contribute to the hardware-aware quantum error mitigation.
mm.
So to mitigate the quantum error, and then that's what I want to do. But all I've done so far is just collect the data set,
Yeah,
and the next steps would be to perform statistical analysis based on the data set.
yeah. Wonderful, wonderful. This is a unique problem you took, and you are pretty close to like find a solution. That's so awesome. Um, yeah. So the quantum error correction is a big topic. So yeah, this can be used there. So it's already past 9. Wonderful, guys. I am really enjoyed working with you, teaching you guys all this like 2 weeks course on this quantum computing, and I'm really happy that you guys picked up a lot. So I am wishing you guys all successful career, successful college, and if you are interested in connecting me, you can connect. I'll post my LinkedIn link in the email that I'm going to send you guys. You can connect with me through LinkedIn, and also you can also send me an email anytime. If you have any suggestions or any questions or anything, if anything you want to discuss, I'm ready to discuss with you guys. So enjoy your rest of your summer holidays. Okay.
All right,
So
thank you.
yeah,
Thank
thank
you
you
so
all.
much.
Bye.
Thank
Okay.
you. Thank you so
Yeah,
much.
bye.
Thank you so much. Have
Thank
a
you.
good summer.